In the previous slide, we discussed the standard combustion enthalpy of methane. Combustion enthalpies are important quantities to evaluate and compare when you study foods or fuels. A standard reaction enthalpy is also important because it corresponds to the heat released or absorbed by a reaction carried out at constant pressure. Standard reaction enthalpies are characteristic properties of reactions and are tabulated in various databases. See, for example, the resource data section at the end of your book for a variety of standard combustion enthalpy data. In a previous lecture, we indicated that the heat absorbed or released by a reaction is typically measured using a constant volume adiabatic bomb calorimeter. However, under constant volume conditions, the heat is equal to the change in energy, not the change in enthalpy. So it would be useful to learn how to relate the standard enthalpy change, delta H standard, to the standard energy change, delta U standard, for chemical reactions. To obtain a relationship between delta H standard and delta U standard, we start with the relationship between H and U. By definition, H equals U plus PV. In a previous lecture, we indicated that for ideal gases, we can replace PV by nRT, and for liquids and solids, which have much smaller molar volumes, we can usually neglect the PV term. So for ideal gases, we write H equals U plus nRT. And for liquids and solids, we write H equals U. From this observation, we conclude that there is only a difference between delta H standard and delta U standard if gases are involved in the reaction, and if the number of moles of gas on the reactant side of the reaction equation is different from the number of moles of gas on the product side of the reaction equation. So we write delta HC standard equals delta CU standard plus delta combustion of PV equals delta CU standard plus delta C of N gas RT, since we are neglecting the number of moles of liquids or solids. Then we use the fact that the chemical reactions are typically carried out at constant temperature, so the change in N gas RT is simply RT times the change in the number of moles of gas for the reaction. Let us apply this result to the combustion of methane at 25 degrees Celsius, for which the reaction equation is given by 1 mole of methane gas plus 2 moles of molecular oxygen gas gives 1 mole of carbon dioxide gas plus 2 moles of water liquid. The change in the number of moles of gas, delta N0 gas under standard condition, for this reaction is 1 for the products, CO2, minus 3 for the reactant, 1 for methane, 2 for oxygen. The result is minus 2. So we conclude delta CH standard equals delta CU standard minus 2 times RT. Let us consider now the combustion of glycine in a constant volume adiabatic bomb calorimeter at 25 degrees Celsius. When we use 3.753 grams of glycine in a bomb calorimeter, the measured heat of reaction is minus 48.48 kilojoules. We would like to know the value that should be reported for the standard combustion enthalpy of glycine at 25 degrees Celsius. First, we write the combustion reaction equation for 1 mole of glycine solid. Glycine has 2 carbon atoms, so we should form 2 moles of carbon dioxide gas. Glycine has 1 nitrogen atom, so we should also form half a mole of molecular nitrogen gas. Glycine has 5 hydrogen atoms, so we should also form 5 half moles of molecular hydrogen gas. Now we can balance the reaction for oxygen. There are 4 plus 5 halves equals 6.5 moles of oxygen atoms on the product side, and 2 moles of oxygen atoms in glycine. So we need to add 4.5 moles of oxygen atoms on the reactant side. So to balance the reaction, we need to add 9/4 mole of molecular oxygen on the reactant side. Next, we recall that the reaction carried out in an adiabatic bomb calorimeter occurs at constant volume. So the heat of combustion is equal to the change in energy for the combustion, which we write as delta C, again C for combustion, U. Note that this is not the standard combustion energy because we would have written delta C U standard, which we would write as delta C U standard, since delta C U standard corresponds to the heat at constant volume for 1 mole of reaction equation. Here we use 3.753 grams of glycine, which corresponds to 0.050001 mole of glycine. So to get delta Cu standard, we need to divide delta Cu for 3.7534 grams of glycine by the number of moles of reaction equation associated with this mass of glycine. Since there's 1 mole of glycine per mole of reaction equation, we conclude that delta Cu standard is equal to delta Cu divided by 0.050001 mole. So we get delta Cu standard equals minus 969.6 kilojoules per mole. To obtain delta Ch standard, we write delta Ch standard equals delta Cu standard plus RT times the change in the number of moles of gas in the reaction equation. Delta N gas standard is equal to 2 for CO2 plus half for nitrogen minus 9/4 for oxygen, which is equal to 1/4. So delta Ch standard equals minus 969.6 kilojoules per mole plus 1/4 times 0.00833145 kilojoules per moles per Kelvin times 298.15 Kelvin. This yields delta Ch standards equals minus 969.0 kilojoules per mole. Note that in the equation for delta Ch standard, we use R equals 0.00833145 kilojoules per mole, since delta U was given in kilojoules per mole. On this slide, I am showing a table containing standard combustion enthalpy data for a variety of organic compounds. Examination of this data allows you to conclude that in general, the larger the molecule, the larger the standard combustion enthalpies, as long as substances exhibit the same oxygen content. Indeed, the higher the oxygen content of an organic molecule, the less oxidation its carbon and hydrogen atoms will require to reach the oxidation levels observed in carbon dioxide and water. Hence, the lower the heat released as a result of combustion. So for instance, the delta Ch standard value for carbon graphite is higher than that for carbon monoxide. Similarly, less heat is released during the combustion of methanol than during that of methane. When comparing molecules such as methane, propane, isooctane, the larger the alkane, the larger its standard combustion enthalpy. However, one should not conclude too quickly that the larger the alkane, the better a fuel it would make. Indeed, comparing substances on a molar basis is not fair, since both the mass and the volume associated with 1 mole of substance increase with the molecular size of the organic compound. Furthermore, other factors such as which phase is stable under ambient conditions, the viscosity of the substance must be considered. To shed more light on these questions, we will discuss fuels in more general terms in the next video.